Hi everyone. Okay, as discussed in the previous video, I mentioned through our YouTube channel, we will be putting videos specially discussing about the past paper questions started from 2019 and then we are going to backwards. But I decided to put this special video because most of the students, especially in the Sinhala medium, the ones who are watching my Sinhala medium videos, they requested about to do a video to teach about what are inflection points and about this concavity test, because this is a new part, a new addition to the syllabus. We know that the syllabus was renamed in 2019 for 19 A-level students. That means in 2017 they added and they removed few parts in mathematics, and under differentiation, the second differentiation or the second derivative was introduced to the A-level combined math syllabus. So I just decided to do a video about teaching you what is an inflection point and about this concavity and the uses of the applications of the second derivative test or the second derivative, simply the second derivative or the second differentiation. Okay, first of all, I'll talk about inflection points, because most of the students, when we ask from them what is an inflection point, they don't have an exact answer. For example, if I recently asked from A-level students who's sitting for this year's A-level 2020 A-levels, what is an inflection point, and his answer was inflection points means when a graph goes like this, when a graph goes like this, this point is an inflection point. His answer was this part is an inflection point, this point is an inflection point. But it is wrong. It is totally wrong, because there is an exact definition for what is an inflection point. Okay, so before going to this inflection point, I'll just teach you what is concavity, what is known as this concavity. The concavity means, we know that this shape, this is a maximum, we call it as a local maximum. I'll use the word maximum. We call it as, if it is a maximum, we call it as this is concave down or downwards. Concave downwards means the concave goes down. So if there's a graph which has the shape like this or this, those are known as concave down. Those are known as concave down. But if we have a graph, which has the shape of a minimum, that means if it has a shape like this or it has a shape like this, then we call it as concave up. We call it as concave up. For example, this is concave down and this is concave up. So this is the concavity of this upwards and this downwards. I'm just writing the shortened term down and up. So this is the concavity. What is the concavity? Like if the graph takes a shape like a minimum, we call it as concave up. If the graph takes a shape like of a maximum like these two shapes, then we call it as concave down. So simple. If it is like this, it is concave down. If it is like this, it is concave up. Okay. Now I'll move to the definition. Of an inflection point. If you Google search the inflection point, they will give the definition as like, what is an inflection point? Inflection point is a point where the concavity of a graph is changed. What is an inflection point? An inflection point means a point where the concavity of a graph is changed. For example, I'm taking a graph like this. It has the shape, it takes a maximum and it moves to minimum and it continues to go like this. It goes to infinity, it goes to infinity. Okay, now look what happens. What I said, if the shape is like this, it is concave down. If the shape is like this, it is concave up. And I then told what is an inflection point. An inflection point means a point where the concavity is changed. A point where the concavity is changed. Now it is clear. From here, from this point to a certain point towards here, we have this shape. That means the shape of a maximum. That means this is concave down. This is concave down. And when thinking about this one, we have a shape of a minimum. That means this part is, we call it concave up. Now it is clear. This part is concave down, this part is concave up. This part is concave down, this part is concave up. So what is an inflection point? Inflection point means a point where the concavity of a graph is changed, and it is clear the concave down nature changes somewhere like here, and then it takes a concave up nature. The concave down nature of the graph changes in a point like somewhere here, and then it takes a concave up shape, or a concave up concavity. That means this point is an inflection point. This point is an inflection point. Why? Because we know the definition of the inflection point says an inflection point is a point where the concavity of the graph is changed. The concavity of the graph is changed. It is clear. This is concave down. This is concave down, and it continues like this. This is concave up, and it continues like this. That means there's no inflection points in here, or no inflection point in here. Clear? So I think now you got an idea about what is an inflection point. So after watching this video, if somebody asks from you what is an inflection point, for God's sake, don't say that inflection point is a shape like this. Like an inflection point goes like this. This is a special situation, a special occasion. I'll just discuss about this at the end of the video. Okay. Now just move. Let's move to differentiation. I'll just draw a quick graph because this is not a video about differentiation. I'll draw a quick graph using differentiation. I'll take this x and this y. Okay. I'll take my function is y equals x cubed minus x squared, and I'm differentiating by x, and I take the first differentiation as y dash, and y dash is equal to 3x squared minus 2x. Okay. Now what we do when drawing a graph, we are supposed to draw the graph of y equals x cubed minus x squared, and then what we do, we equals y dash into 0, because to find the turning points of the graph. Because I'm just doing this quickly because this is not a video about differentiation. This is a video about inflection points and about the applications of the second derivative. Okay. So when we equals this to 0, we get 3x squared minus 2x is equal to 0. That means x is common, 3x minus 2 is equal to 0. And I get two turning points. One is x equals 0 and the other one is x equals 2 over 3, x equals 2 over 3. Now we know how to find whether this is a minimum. From here, use the word local minimum, because in the syllabus they have mentioned, clearly stated, when you are teaching this to a student, mention the word local, because we know after drawing this graph, I'll just show you that this is not the exact minimum of the graph. If this point is minimum, we should mention it as a local minimum, because this is not the exact minimum of the graph. If this is a maximum, we have to mention it as a local maximum, because this is not the exact maximum of the graph. I'll describe about it when I draw the graph. Okay, so we know how to find whether this is a maximum, local maximum or local minimum using the first differentiation. So I'll teach you how to get it by the second derivative. That means the applications of second derivative, Okay, then let's move. And I'm finding the second derivative. The second differentiation, which means 3x squared we differentiate, we get 6x and minus 2. We get minus 2. In the first step, we got that there are two turning points in the graph. One is x equals 0 and the other one is x equals 2 over 3. So what is the theory? I'm putting a red star mark to the theory. The theory says if we get x equals a as a turning point, which means in a here is equal to 0 or 2 over 3, the theory says when we substitute this turning point's value to the second differentiation, and if we get a positive answer, that means we call it as concave up. We know what is concave up. Concave up means a shape like this. Which means if this is greater than 0, we get a minimum. We get a local minimum. We get a local minimum. Local minimum. And if y double dash a is less than 0, the theory states that means the shape is concave down. The shape is concave down, which means the shape goes like this, and then we know that it is a local maximum. It is a local maximum. So what we should do, first find the turning points by using the first differentiation, using the first derivative. Find the first derivative, equal it to 0, and then we get two turning points. And by using this theorem, what if we substitute the turning point to the y double dash to the second derivative, is if it is a positive one, so if it is greater than 0, we have a shape of concave up, which means it's a local minimum. If it is less than 0, we have a shape of concave down, which means it's a local maximum, okay. So now I'm going to use this to find whether these turning points are local minimums or local maximums. Okay, then I'm starting with x equals 0. I get y double dash 0 is equal to 6 into 0 minus 2. Y double dash 0 is equal minus 2 less than 0. Minus 0 is less than 0, which means at x equals 0, we get a local maximum. We know when x equals 0, the y is 0, that means we have a local maximum here. The other point is 2 over 3. Then I'm substituting x equals 2 over 3. I get y double dash 2 over 3 is equal to 6 into 2 over 3 minus 2. This is 2 equals 2. 2 is greater than 0, which means at x equals 2 over 3, we get a local minimum. Then when we substitute x equals 2 over 3 to this one, we get a minus value. Just substitute and check it. We get a minus value somewhere around minus 427. So at x equals 2 over 3, at x equals 2 over 3, I get a local minimum. So we can join the graph. It goes like here, and find the limit of y when x tends to minus infinity. Find the limit of y when x tends to minus infinity. You will get it as y goes to minus infinity. You will get it as y goes to minus infinity. Then find the limit when x tends to positive infinity plus infinity. Then you will get y goes to positive infinity. So the graph continues like this. Okay. Now what I did, I apply the second derivative. The nature of the second derivative to find whether these turning points, I got the turning points by equaling the first derivative is 0. I got the first derivative, and to find whether they are local maximums or minimums, what I do, I'm using the second derivative test. What does the second derivative test say? It says that if when we sub the turning point to the second derivative, if we get a negative answer, that means there's a local maximum at that point. If we get a positive answer, that means we get a local minimum at that point. Very clear. Now I'll just refresh your knowledge about an inflection point. What is an inflection point? An inflection point is a point where the concavity of a graph is changed. An inflection point is a point where the concavity of a graph is changed. Now just pay your attention. You get this as concave down. You get this as concave down. You get this as concave up. You get this as concave up. Which means going from concave down, in somewhere around here, at a point somewhere around here, the concavity of the graph has been changed. From concave down to concave up, which means there is an inflection point here. There is an inflection point here. There's an inflection point here, because at that point, the concavity of the graph has been changed. The concavity nature of the graph has been changed. From the definition of an inflection point, we can determine that there's an inflection point at this, somewhere around here. So somebody might get a question. We have drawn graphs where when we consider y dash equals 0, when we consider the first differentiation is equal to 0, at some position, not only we get all the time, we get local maximums and local minimums. Sometimes I get inflection points. But at this one, I didn't get an inflection point. I only got a local maximum and local minimum. But according to the definition of the inflection point, it is clear that there's an inflection point here. It is clear that there's an inflection point here. I have told this before. If there's anything important to you, you can just pause the video and just write it down. Just write it down. Okay, pause the video and write it down. Okay, and then I was talking about this concave nature and inflection point. Why didn't we get this inflection point? So there's an inflection point between 2/3 and 0. Why didn't we get that inflection point by using the first when we make the first differentiation equal to 0? When we make the first differentiation equal to 0, why didn't I get that inflection point? The reason, if we get a inflection point by this, which means if we get an inflection point by making the first differentiation equal to 0, we know what is the first differentiation. If we consider a graph like this, the first differentiation means the gradient of the tangent drawn to any point of the graph. The first differentiation means the gradient of the tangent drawn to any point of the graph. So it is clear. In here we are considering that the gradient is equal to 0. I know the gradient is equal to 0, which means it is a line parallel to the x-axis. So it is clear, if it is local maximum, if it is a maximum, here the tangent is parallel to the x-axis. If it is a local minimum, the tangent is parallel to the x-axis. So if we are getting an inflection point from this one, from when we consider the y dash equals 0, or when we make the first differentiation equal to 0, if we get an inflection point, that inflection point only has a nature like this or this. That inflection point only has the nature like this or this, which means at a certain place the graph becomes flat. At a certain point the graph becomes flat. Why? I know then only the tangent drawn at that point, becomes 0. Then only the tangent the gradient of the tangent drawn at that point becomes 0. So all the inflection points don't have a nature like this, don't have a shape like this. The inflection points which has a gradient of 0, the inflection points which have a gradient of 0 only show this nature, So I think you got a clear idea about what is an inflection point, what is concave up, what is concave down, what is the concavity, and how to find the local maximums and local minimums using the second derivative test. Okay, now let's move how to find an inflection point. Let's move to how to find an inflection point. It is clear. The theory states, this is theory part. I'm using a red star to the theory. If there's any point, if there's any x value such that y double dash is equal to 0, the theory says if there's any x value such that y double dash is equal to 0, that point can be an inflection point. The theory doesn't say that it is an inflection point for sure. The theory doesn't say indefinitely that this is an inflection point. The theory says if there's any x value which gives y double dash equals 0, that point can be an inflection point. That point can be an inflection point. So I'm considering y double dash equals 0, which means 6x minus 2 is equal to 0. X is equal to 2 over 6. 2 over 6. X is equal to 1 over 3. So, according to the theory, 1 over 3 can be an inflection point. It is not indefinitely. It is not an inflection point. It can be. It can be. We can't be 100% sure that this is an inflection point. It can be an inflection point. So, what are we doing to show that this is an inflection point? I know that inflection point, if it is an inflection point, at that point, the concavity should change. If it had a concave down nature before the point, after the point it should have a concave up nature. If it had a concave up nature before the point, after the point it should have a concave down nature. So we have to show that from at this point, we have to show that at this point the concavity changes, the concavity of the graph changes. So what I do, I just take a value somewhere here, I'll take 0, and I know to find the concavity, I'm using the second derivative. I'm using the second derivative. So when I consider I'm taking 0, I'll get y double dash is 0, and I get 6 into 0 minus 2, which equals minus 2. It is negative. It is clear it is negative, which means the second derivative is negative at this region, which means they give us, I know if it is negative, we have maximum, that means concave down. Before 1 over 3, the concavity is concave down. And I'm taking a point after 1 over 3, I'll take x equals 1. Then I'm considering the concavity 1. It is clear, it is 6 into 1 minus 2. Minus 2, I get the answer. 6 minus 2, 4, I get the answer, which is a positive number. So the second derivative is positive in this region, which means positive means a minimum shape, which means it is concave up. So now I'm clear. Before 1 over 3, I had a concave down nature. And after 1 over 3, I have a concave up nature. So I can write which means x equals 1 over 3 is an inflection point. So it is clear in this one. I mentioned then I can see a concave down nature here and I can see a concave up nature here, which means there should be an inflection point in between this. We have found that the inflection point is x equals 1 over 3. We have found that the inflection point is x over 3, which means this inflection point is 1 over 3. But I'm repeating the thing. If the inflection point, if the first derivative at the inflection point is equal to 0, which means if it is a turning point, then only the inflection point goes like this. If the first derivative at the inflection point is not equal to 0, then the inflection point just continues like this. We can't find any defect in here. We can find any defect or like a deformation at the inflection point. It just continues. See, I can't find a deformation. The graph just continues. But I know that the concavity has changed. That means from concave down to concave up, which means this is an inflection point. Okay. Now, so I'll just now on the screen you can see I'll display the 2019 AL paper, the differentiation paper, and the second part of under the A question number 14, the A part, second one, they have given us if it is given that f double dash x is equal to this, find the x coordinates of the point of inflection of the graph. We are supposed to find the point of x coordinates of the point of inflection. So it is clear now in the marking scheme, for making y double dash equals 0, we get 5 marks. So this is not the final answer. We can't state this as the final answer. We are just finding this can be an inflection point. Okay. For that we only get 5 marks. For showing that, like I had this what we had is, I showed that before 1 over 3, I took a value of 0 and I sub it to y double dash, and I got that before 1 over 3 I have a concave down nature, and after 1 over 3 I have a concave up nature. After 1 over 3 I have a concave up nature. So it is clear, before this point it is a concave down, which means a negative second derivative. After this point is a positive second derivative, which means concave up. So it is clear from at this point, the concavity has been changed. For this one we get 10 marks, for this one we get 10 marks, this one 5, and write in, therefore x equals 1 over 3 is an inflection point, we get another 5. So we have got 20 for this part. But unfortunately, most of the students are taught that if there's any x value which gives y double dash equals 0, definitely that it is an inflection point. Most of the students are taught that one. That is totally wrong. The theory states if there's any x value which gives y double dash equals 0, that point can be an inflection point. For that one we get 5 marks. To showing that it is an inflection point, we get the remaining 10 marks. So if any student is taught that by making y double dash equals 0, or if there's any x which makes y double dash equals 0, that is an inflection point, that student will find this one and stop the answer. He will lose 15 marks. So for the A-level paper, if we get something like this, we have to do we call this as a concavity test. Find the concavity using the second derivative. We have to find the concavity before the point and after the point. So it is clear. I'll give a quick revision. I'll give a quick summary about the video. If you are interested, you can note down. If you are interested, you can note down what I said. What is it? If I'm given a graph y equals fx, the first step is to find y dash, and then we have to make y dash equal to 0, and from that we get the turning points of the graph. Even though we use the first derivative method using the gradient to check whether these are local maximums or minimums or inflection points, even though we use the second derivative method, the first step of both of the methods is to make in y dash equal to 0 and find in the turning points, because to check whether the turning points are maximums or minimums, so first we have to find them. So we have to find the turning point. This is not a differentiation video. So I hope that you know about how to find whether it is a local minimum or a local maximum using the first differentiation. What I needed to teach here is using the second derivative method. So what happens in the second derivative method? Find the second derivative, and when you sub this turning point, if it is a positive answer, the concavity, which are concave up. The concavity, we can say it as concave up, which means concave up means it gives a local minimum. Write in the word local is a must. And if y double dash is less than 0, the concavity is concave down. Which means at that point we get a local maximum. What was the final one? Final one is finding the inflection point. To find the inflection point, we have to check whether there's any x value which gives y double dash equals 0. We have to check whether there's any x value which gives y double dash equals 0. If there's any point, we say that point can be an inflection point. To confirm whether it is an inflection point, we have to do the concavity test. Check the concavity by substituting any value before that point. If it was according to the graph v draw, it was 1 over 3. So take a value before 1 over 3 and sub it to the second derivative. And if you get a like as example, we got this region as a negative second derivative, which means before 1 over 3 we have a concave down nature, and after 1 over 3 I got a positive second derivative, which means the concavity is concave up. So it is clear at this point the concavity has been changed, so we can confirm, we can make sure that this is an inflection point, and that is the way how to find an inflection point. So you may have done some graphs that where we can get the inflection point from the second differential, from the first derivative, but most of the inflection points we can't get them from the first derivative. We have to find the second derivative and we have to make it equal to 0 and do this test to find an inflection point. And as I mentioned, if we get an inflection point from the first derivative by making the first derivative equal 0 in such an inflection point, the graph goes like this. For a smaller period, the graph becomes flat. Because then the tangent drawn at that point becomes horizontal, which means the gradient is 0. Because if we get a inflection point by getting the gradient or the first differentiation equals 0, that means the gradient of the tangent should be equal to 0, which means the gradient of the tangent should be equal to 0. So if we get an inflection point using the first derivative is equal to 0, we have to draw that inflection point clearly like this. But if we get a inflection point by only when we get y double dash equals 0, and if that was not equal to 0 when considering its first differentiation, the graph just continues like this. As the graph we did, there was a concavity change here. It is concave down to concave up, but there's no deformation, there's no defect in the graph. The graph just continues like this. So I did this special video, just deviating from the past papers we used to do, to give you, because most of the students requested me, like they haven't given a proper understanding about the second derivative, how to find the local minimum, how to find the local maximum using this the second derivative. So I just decided to do this video to give an idea about what is an inflection point and how can we do the concavity test, what is an concavity, and by using the second derivative, how can we find an inflection point. And I just mentioned how can we get an inflection point even by considering the first differentiation is equal to 0. So this is the summary. Just if there's anything important, you can just pause the video and note down. So join with us in our next video. Next I will be discussing a new addition to the syllabus. The new addition is we know by using integration, we can find the volume of an a rotating disc. If we get a specific area and we rotate it around the x-axis by 360 degrees, we get an object, we get a volumetric object. Finding the volume using integration. It is a new addition to the syllabus, and it will be discussed by using the 2019 integration past paper first part question. By using the 2019 PO Maths paper first part question under integration, I will be discussing it, and it is a new addition to the syllabus. And even this one, the second derivative test, was also a new addition for the syllabus. Okay. So I hope that you got a clear understanding about what is an inflection point, what is the concavity, what is concave up, what is concave down, and what are the applications, how is the second derivative is used.